If you look at decentralized power, solar panels dominate the landscape. They make up roughly 90 to 95% of all off-grid energy supplies, an entrenched default choice that dates all the way back to the 1970s. This chart shows the seasonal weakness of a pure solar setup. The yellow line tracks solar production, and what winter solar provides creates a huge financial problem. Homeowners are forced to over-purchase thousands of dollars in lithium batteries just to survive those dark months. Wind solves this through sheer physics. A single cubic yard of air moving at 20 miles per hour contains a significantly higher kinetic energy density than the flat photons hitting a solar panel of the exact same size. Naturally, most people write off home wind power. The industry has conditioned us to picture 60-foot steel towers, strict zoning violations, and fragile blades that rip apart in a storm. We will bypass the standard industry catalog and map out 6 highly specific wind geometries designed to solve those exact problems, evaluating them purely on your property constraints and local climate. The goal isn't to replace your solar array. By integrating wind to work the night shift, you can reduce your chemical battery storage requirements by up to 40%. In a standard neighborhood, passing air constantly ricochets off houses, fences, and trees. This creates highly turbulent, swirling gusts that rob traditional horizontal propellers of their efficiency. This chart plots our first category of turbines in the bottom left quadrant. They offer modest power output, but they require nearly zero installation difficulty or zoning battles. The Tessup Atlas handles urban turbulence by ditching the propeller entirely. Its aluminum scoops loop vertically around a central axis, creating a 360-degree catchment area that harvests kinetic energy from any direction without needing to rotate its body. Traditional blades have to move faster than the wind, creating a high-pitched slicing noise. The Liam F1 tackles that by using a conical, spiral geometry. Acting like a classic Archimedes screw, the Liam catches the moving air, redirects it 90 degrees, and slows it to almost zero by the time it exits the back. This drops the operational noise to below 45 decibels, making it quieter than your kitchen refrigerator. Flower turbines take a similar approach with curved vertical blades. Because they spin at a lower tip speed and form a solid, visible cylinder in the air, animals see them as a physical obstacle, completely eliminating the danger of bird strikes. Their shape also exploits a fluid dynamics quirk called the cluster effect. The turbulent air shedding off one spinning turbine acts as a mechanical gear, actively catching and accelerating the blades of the unit next to it. The financial trade-off is volume. To generate serious power with these setups, you need to invest in multiple modular units to build an interconnected, high-density microgrid on your roof. In restricted neighborhoods, you give up the massive raw wattage of a 60-foot tower in exchange for stealth geometry, allowing you to turn local zoning codes from a barrier into a design parameter. Some locations are outright hostile. If your property faces corrosive coastal salt spray, high-altitude mountain ridges, or sub-zero blizzards, standard residential turbines will simply shatter. Survival here requires understanding baseline energy load. You don't need massive peak wattage during a storm. A steady 150 to 400 continuous watts is enough to keep your deep freezers online and maintain vital communication systems when solar panels are blind. The Primus Air series was engineered for the brutal maritime industry. Built with aircraft-grade aluminum and carbon fiber blades that flex under pressure, it miniaturizes the standard wall-sized cabinet of charge controllers by building the electronics directly into the rotating turbine body. On the chart, this category moves to the far left for total output, but maximizes a new metric for extreme weather survivability. For environments like the Great Plains or Iceland, where winds can scream up to 130 miles per hour, the Icewind turbine uses a sophisticated dual-blade geometry. Inner scoops provide massive starting torque in low wind, while outer aerodynamic blades take over at high speeds. Instead of hanging fragile gearboxes in the freezing rain, the Icewind places its heavy direct drive generator at the absolute base of the unit. It is completely enclosed, with no exposed gears or external wiring to freeze over. Out here, raw wattage figures are useless if the machine breaks. You are paying a premium for uncompromising mechanics that operate untouched for decades. If you have unrestricted rural acreage and consume over 10,000 kilowatt hours a year, microgenerators won't make a dent in your utility bill. You need utility-scale power. But at this scale, A fried motherboard or a broken sensor leaves you stranded with a frozen machine and a massive maintenance bill. The SD6 from Scotland strips away those electronics. It uses a downwind architecture where the wind passes the tower before hitting the blades, allowing natural air currents to pull the turbine into alignment without a single electric motor. During severe gales, standard turbines rely on active digital braking systems to shut down completely so they don't tear themselves apart. The SD6 never shuts down. It uses a purely mechanical centrifugal force system called a delta rotor. As wind speeds accelerate, if physical pressure causes the composite blades to automatically twist backward, naturally shedding excess force while continuously generating power safely. This level of engineering requires serious capital. Between the hardware, a hydraulic monopole tower, and the required concrete foundation pour, total installed costs land between $25,000 and $35,000. That plots our final category at the extreme top right of the chart. It carries the highest upfront capital requirements, but delivers the absolute highest annual energy yield. If you have the land and capital, true power comes from rejecting fragile digital components and investing in heavy-duty machinery capable of zeroing out your bill completely. None of these options matter if you do not have the right conditions. You cannot guess your wind speed by standing outside, or you will end up wasting thousands on a system anchored in a dead air zone. Your first required step is installing a digital data logging anemometer at your intended mounting height. Let it record for 6 to 12 months so you have hard data on your property's exact seasonal patterns. This flowchart maps out the decision. The top node is your property type. Everything splits based on whether your space is restricted or unrestricted. If you live in an urban or suburban setting, the need to avoid noise complaints and zoning laws pushes you down the left path, straight to the TESUP, Liam F1, or flower geometries. If you have rural acreage, the path splits again based on your climate. You choose between extreme weather survival systems like the Icewind and Primus, or maximizing raw output with the SD6. Utilizing specific geometries to catch the passing atmosphere is the oldest trick humanity has for generating free, reliable mechanical power. The 200 trillion kilowatts of kinetic energy spinning over your roof every single day is an untapped financial asset. By pairing the heavy kinetic force of the wind with the quiet consistency of your solar panels, you can naturally fill the gaps in your production. You step off the battery upgrade treadmill and secure round-the-clock power on your own terms.